Hello everyone. For your attention, here is a presentation on prospects for autonomous low-power renewable energy communities by Yurii Veremiichuk, Vitaly Opryshko, Ivan Pritiskach, and Olena Yermoluk from National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnic Institute. In this presentation, we will provide an overview of Ukraine's renewable energy landscape, outline our mathematical modeling approach for renewable energy communities operation, present results on achieving renewable energy communities autonomy through capacity optimization, and discuss implications and recommendations for fortifying energy autonomy. In Ukraine's energy landscape, renewable energy sources are on the rise, notably solar and hydropower. Solar power plants, particularly in the 10-50 megawatt range, dominate the market, followed by smaller plants between 5 and 10. Wind energy lags due to the high cost and complexity. Small-scale producers mirror this trend, with solar power plants leading at 122 megawatts, followed by small and micro hydroelectric plants at 47 megawatts. Across capacities, solar power plants dominate, followed by mini and micro hydroelectric plants. Ukraine's energy reforms prioritize distributed generation, aligning with the European Union's directives. This study aims to optimize small renewable energy sources plants, enhancing energy security and autonomy, with further research focusing on modernizing energy system for societal and economical benefits. As the energy sector in Ukraine undergoes significant reforms, there is a compelling need to cultivate distributed generation and align with the principles of the European Union's fourth energy package. This has paved the way for the emergence of renewable energy communities as a contemporary decentralized solution. Our research aims to address three key objectives. First, we explore strategies to ensure the autonomous operation of renewable energy communities. Second, we delve into sustainability of this autonomous system, particularly during conditions of autonomy or blackouts. And third, we focused on optimizing existing hybrid power systems that incorporate diverse renewable energy sources such as solar, wind, hydro, and biogas. Ultimately, our overreaching goal is to devise strategies that fortify Ukraine's energy security by maximizing the potential of renewable energy communities and hybrid system, thereby reducing dependence on centralized network and fostering a resilient decentralized energy infrastructure. This model on the slide encapsulates the operational dynamics of low-power hybrid renewable energy systems, considering mode characteristics of generation sources, a set of objective functions, and technical and economical constraints. The model facilitates optimal load distribution among system components. Addressing the complexities associated with solving optimization problem or making optimal decisions involves overcoming significant challenges, with a key difficulty being the conceptualization of a reasonable optimality principle. For multi-criteria decision-making problem where the concept of vector optimum is not defined, there is no singular optimality principle. The only viable approach to tackling this challenge is to narrow down the Pareto region. Recognizing the multi-criteria nature of the optimization problem, we employed the Bellman-Zadeh method, grounded in principles of fuzzy set theory. This method offers several advantages. First, it allows for the simultaneous consideration of quantitative and qualitative factors with the ability to distinguish their relative importance. Second, it provides a clear and logical definition of the optimality criterion focused on maximizing the achievement of all target functions. And third, it guarantees that the solution obtained belongs to the Pareto optimal region, representing the most harmonious solution. Through the iterative process, the method derives a fuzzy solution, which is then diffusified by selecting the alternative with the highest degree of membership, representing the optimal decision. By incorporating this robust multi-criteria decision-making approach, our methodology aims to strike a balance between reliability, cost, and environmental considerations, ultimately optimizing the operation of renewable energy communities for enhanced energy autonomy and security. To evaluate the feasibility and implications of achieving autonomy for renewable energy communities in Ukraine, we conducted simulations across 4 distinct renewable energy sources communities. These structures were delineated by varying the ratios of installed capacities among different types of generation sources, namely solar photovoltaic plants, micro hydropower plants, and biogas plants. Our first set of simulations explored the scenario of achieving autonomy for the renewable energy community by augmenting the installed capacity of biogas generation. We conducted simulations with variations in the installed capacity within the range of 50% to 200% of the current capacity levels. On this slide, you can see the optimal loading profiles under the initial conditions where the community relies on the external grid to meet a portion of its energy demands. In contrast, this slide depicts the optimized operation mode under the conditions of achieving autonomy through the increased installed capacity of biogas generation. This mode ensures that all the consumed electricity is generated within the community, eliminating the need for external power flows. These results underscore the significant capacity investment required to transition towards energy self-sufficiency, especially for communities with a large reliance on biogas generation. Next, we explore an alternative scenario to achieve autonomy by augmenting the installed capacity of solar photovoltaic plants within the renewable energy community structures. Our simulations involved varying the installed solar capacity from 150% to 500% of the current levels, and here are the results of our finding. However, similar to the biogas scenario, our results indicate that autonomy remains untenable for the type 2 and type 4 structures, even with a 500% increase in the installed capacity. This slide displays the optimized loading profile under the initial conditions where the community relies on the external grid to supplement its energy needs. In contrast, this slide showcases the optimized operation mode after achieving autonomy through the increased installed capacity of solar generation. This mode demonstrates how the community can meet the entire electricity demand slowly through its own renewable energy sources without drowning power from the external grid. The results from our simulations and optimization analysis shed light on the feasibility and implications of achieving autonomy for renewable energy communities in Ukraine. While these capacity increases may seem daunting, it's essential to recognize the potential benefits of achieving energy autonomy through resilient renewable energy communities by reducing dependence on centralized networks and maximizing the utilization of local renewable sources. These communities can enhance supply chain reliability, bolster regional energy security, and foster local economical growth. In conclusion, our research has shed light on prospects and strategies for achieving autonomous operation of renewable energy communities in Ukraine, aligned with the ongoing energy sector reforms and the transition towards decentralized resilient systems. Through rigorous simulation and optimization analysis, we have demonstrated that attaining energy autonomy for certain renewable energy sources community structures is indeed feasible, albeit requiring substantial increase in installed generation capacity. And thank you very much for your attention.